everybody, and welcome to Echo Live. My name is Anna, coming to you from the Michigan Science Center's Echo Distance Learning Program. And today, we heard you, we are talking about crystallography and the study of crystals. So this is a suggestion that we got from our audience. I know that quite a few of you have been asking for an episode about crystals. So I've done my best here. I will admit I am no geologist, but I found a lot of things really interesting about crystals and about gems and minerals that I'd love to share with you guys all today. So we've got some crystal growing experiments, but I'd love to talk just a little bit about the background of crystals. Before we get started with the show, as always, go ahead and introduce yourself in the chat feature of whichever program you are tuning in on. I know that we have some friends joining us from YouTube. I know we've got some friends joining us on our Facebook Live page, and of course, our friends here in our handy dandy Zoom meeting. So everyone, welcome. Introduce yourself in the chat because that is a great way for you to communicate with me throughout the program. You can use it to ask questions, to answer questions, and to make suggestions for future experiments you might like to see us try here on Echo Live. All right, so let's get started talking about crystals, right? You can see that I have some examples of crystals up here on the table. So let's take a zoomed in look at just a few of these crystals that I brought with me today. Now, I have quite the crystal collection of my own. I've been collecting gems and minerals and other types of rocks ever since I was a little kid. And this is just a small part of my rock collection that I wanted to show you because I do find these things really interesting. And I found that there's some pretty cool science behind them as well. Lots of people saying that they like my background. Thank you. I like this one as well. This is an example of a crystal right behind me. So the first thing we should address, right, is what exactly is a crystal? What makes a crystal and not just a rock or some other sort of substance? Now, what makes a crystal is its structure, the arrangement of the atoms inside these compounds. We say that they have a crystalline structure, which is exactly where crystals get their name. You'll notice that in a crystalline structure, those atoms and molecules have a very regular, uniform arrangement. So the arrangement throughout the entire crystal is the same. So it doesn't change. We used another word for this kind of mixture when we were talking about mixtures on a past episode of Echo Live. We called those mixtures that are uniform throughout, we called them homogeneous. That's usually when we're talking about mixtures of different things. But crystalline structures are repeating patterns of the same atoms over and over again, and they're locked into place in this very specific type of structure. On the other hand, right, we have non-crystalline arrangements of atoms, and you can see that it's not the same throughout. There's lots of gaps in between as these atoms have kind of formed their shape. But it's not identical throughout. You can't find a repeating pattern. So crystals always have a repetitive pattern, whereas non-crystalline substances do not. Now, in crystals, we say that there are 6 basic crystal systems or arrangements, but there are 7 here on this diagram, and we'll talk about the very last one. The very last one over on the side, that one is trigonal, but that one we'll talk about at the end because it's a kind of a special case. But basically, when these atoms inside crystals arrange themselves, they follow one of these 6 uniform arrangements. So we have isometric, which we might also call cubic. If you've heard of cubic zirconium, of course, follows an isometric or cubic arrangement. We also have tetragonal. We have orthorhombic. We have monoclinic. We have triclinic, and we have hexagonal. Now, these are big, long words that did take me a little bit of practice to make sure I was going to pronounce correctly for you. But basically, these arrangements are what we get once those atoms start to form these repetitive patterns. So underneath each of these types of patterns, we have an example of a crystal that also follows that pattern. So we said that cubic zirconium, which is a lab-grown crystal, is cubic or isometric, but so is fluorite. A tetragonal that follows this shape, which is not a cube, but more of a rectangle, a four-dimensional rectangle or three-dimensional rectangle. We have wolfenite. Orthorhombic gives us tanzanite. Monoclinic gives us azurite. Triclinic gives us amazonite, which I think is pretty beautiful. I love the color of that one. Emeralds, which I'm sure we've all heard of before. They're these beautiful green crystals or gemstones. They are hexagonal. And then we said trigonal is kind of a unique case. Now, trigonal usually just means that they come to a point at the top. We sometimes call quartz a hexagonal trigonal crystal, but we'll mainly worry about these first 6 formations of crystals. Now, I've got crystals down here on my table. So I'd like to take another close look at them and talk about what they are. The first ones I'd like to talk about are kind of this grouping of gems that I have right over here. Let me zoom in even further so we can get a really up close look. Wrong side. There we go. All of these crystals are actually the exact same type of stone. So these are all they're all actually the same type of stone. But what you'll notice is that they are all different colors. So let's talk about why this is. All of these stones are examples of quartz. I'm sure we've heard of quartz before. Quartz is a very, very common type of crystal. It grows in a hexagonal structure. So you can see, especially with this pointed piece of quartz here, that it has 6 sides. If I hold it towards the camera, it's a bit easier to tell. So quartz grows in a hexagonal structure, but we can get it in all of these different sorts of colors, and it comes in many more colors than just this. Now, can anyone identify this specific type of quartz? A lot of people might know what it is. This is a very, very common gemstone. If you're a fan of crystals or minerals like I am, you might know what we would call this one. What would you call this if you had to identify it? Anyone familiar with crystals out there? I'd love to see if anyone knows what this one is. Now we know it's a type of quartz. It is certainly a type of quartz, but there's another common name for this specific color of quartz. It's not fluorite. Courtney tells me this is an amethyst, and you are exactly right. Now we can see that it's forming all sorts of these hexagonal crystals, right? So each individual one, but they grow normally in big clumps like this. And then sometimes we separate them to have them be sold, or we cut them in their kind of shapes so that we can sell them, because they're very beautiful when they come like this. But this is actually how we normally would find clumps of quartz. So we call this kind of coloring of quartz, we call this an amethyst. So amethyst is just a violet colored quartz. So it is still just quartz, but why is it purple? Now purple, quartz, if it was clear, oh man, camera, don't do that to me. But if I put my hand here, it'll help. There we go. All right, so our violet quartz happens because there are impurities in this crystal. So here we have some clear quartz. This is what quartz would look like if it was totally pure. You can see that it still grows in those hexagonal points, but this is clear quartz. This one has a little bit of impurity in it, and so you can see it's got kind of some yellowish color in there. But the impurities in amethyst are actually what allow us to get that purple wavelength of visible light being refracted through it. So if it was pure, it would be clear. But the impurities in amethyst will actually change or refract the frequency of light as it travels through this gem. And then it comes to our eyes in the form of violet visible light. So these are the same type of crystal, but this one has impurities that cause it to be purple. So if you were to call this violet quartz instead of amethyst, you would be still correct. We also have this, which some people would call green amethyst. And that sounds kind of funny, right? Because amethyst is actually the name for the purple color, but this is green quartz. And the way we get green quartz is actually by taking amethyst and heating it up. And if you heat the impurities in this violet quartz to a really, really high temperature, some of it will turn orange or yellow, But depending on the temperature and the properties of your crystal, sometimes you can get this really, really beautiful light green color. So I think green quartz is very beautiful, but I think that's because green is my favorite color. But there are also impurities in other kinds of quartz that could give us this pink shade as well, which we call rose quartz. So all of these minerals right here, these are all examples of quartz, but they have different colors based on the impurities inside them. Now, I want to talk a little more about those formations of crystals. So I have an animation to share with you that comes from TED Education, but they do a really good job of showing us why these different types of crystals, depending on what types of atoms they're made of, why they grow into different shapes or based on their environment. So let's take a look at this animation here. So this is an animation, kind of an animated picture of something called galena. And galena is isometric or grows in a cubic formation. So even when you find this, instead of being shaped like little hexagons like our quartz crystals, these grow in cubes. Which make them really, really beautiful. So if you ever do find one, that would be amazing. Definitely keep it and hold on to it. But let's take a look at a molecular level or at an atomic level, what gives galena its shape. So as we watch this animation, pay attention to the arrangements of these two molecules now, or these two atoms. So we've got two kinds of atoms here. Does anyone happen to know what atom is signified by Pb? Anyone know what Pb stands for on the periodic table? I'll give you a hint. It is not peanut butter. But Pb is an element on our periodic table. It's one of the things we would find in one of those tiles on our periodic table. Does anyone know what Pb stands for? Once you've guessed Pb, you could also tell me, do you know what S stands for? Some good guesses. Yeah, Evan tells me that Pb stands for lead. Good job. That one's a little confusing, right? Why Pb? But so Pb represents lead atoms and S represents sulfur. So let's go ahead and take a look at how lead and sulfur atoms give us galena crystals. So watch how they arrange themselves. We can see that we've got 4 lead atoms that form this square shape. And next, we're going to have our sulfur atoms bond to those lead. So now we've added another layer. And you'll notice that like in any crystal, we said these structures are repetitive. So once I hit play, watch as this structure repeats over and over and over again. And there's only one shape this arrangement could possibly give us. As they arrange and as they bond in that exact specific orientation, as they collect more and more atoms from their environment where these crystals are formed, they form cubic or isometric crystals. Let's take a look at a different one. Next up, we have quartz. So this might look just like that rose quartz point that I showed you. And this is the atomic structure of those crystals. So they start off, we have silicon surrounded by oxygen atoms, and then that structure repeats itself to form into this hexagonal structure. Now, crystals come in all sorts of colors, but they can also change their color or their orientation based on the environment that they grow in. Most of the time, our crystals don't have enough space to grow into massive quartz points. So it's pretty rare to find a really, really well-shaped quartz point that looks just like this, because normally there's all sorts of other crystals and minerals forming all around it. So they don't always have enough space to grow very large, but sometimes they do. But when they don't, we get something more like these. And you might have noticed these on the table that they don't really look like crystals, do they? These just look like regular old rocks. And I wanted to show you guys these because sometimes crystals, we don't stumble upon them in their most beautiful form. Sometimes, most of the time, we have to chip away at the outside of these minerals. We cut them, we polish them to reveal some more beautiful compounds on the inside. So these are what we call geodes. So geodes look like this. They're kind of just shiny, light brown rocks that if you were to see this laying on the ground, you might not think much of it. But what's special about these rocks is that inside them, they had the perfect condition to form a combination of quartz and agate crystals. So if you were to take this rock, which is actually why I bought this rock, and smash it with a hammer, you would get something like this. On the inside of these geodes, we have crystals forming into those really, really beautiful crystalline formations. So I've got a different type of geode here. This is a different type of geode. These are from different parts of the world, and so they look very different on the inside. But this is normally, or more commonly, what geodes or crystals would look like, right? It's kind of a mess. We've got lots of tiny little crystals forming, but since they don't have enough space to grow really, really large, most of the time crystals look like this. Large crystals are, of course, much more rare because they need much more space to grow, and that doesn't happen very commonly in nature. There's all sorts of minerals in the soil and in the Earth's mantle, and so we normally get something more like this. So if you're lucky enough to find a big amethyst or a big quartz crystal, think about the amount of time that it took in order to grow that crystal and the perfect conditions that had to exist in order for that crystal to be formed. So crystals are, they're uniform, right? But they are unique because they all grow in their own set of conditions and they all grow according to their environment. So I've got a couple more examples to show you. And then of course I want to do an activity that you can try at home. So in this plastic bag, I do have a crystal, but I want you to take a look at this and you'll probably be able to figure out why I keep it in a bag. I could probably look into getting a little bit more secure type of way to store this, but I have so many rocks that sometimes it's hard to give them all an adequate amount of space. But this is a crystal and it's actually not quartz. It looks very similar to quartz in color. So it is white and the shape is not exactly the same, but this is actually a salt crystal inside this bag. And why this is so special to me is that this is actually salt from the Great Salt Lake out in Utah. So on a trip that I took out to the Great Salt Lake, there was a local artist who was selling crystals that they had grown from the salt inside the water. So we'll talk a little bit more about how that process actually works. But the only way that these crystals were able to be formed was through evaporation. We wanted those salt atoms or those salt molecules to form this crystalline structure. Now, because of what they're made of, since these are made of salt as opposed to some firmer materials like our silicon that forms our quartz crystals, it's very, very brittle. It's not very strong. But we were able to grow this because of how high the salt concentration is inside the Great Salt Lake. Does anyone happen to know by what percent is the Great Salt Lake salt? Anyone know just how salty by percentage? Does anyone have a guess? I'll give you a hint. The ocean, or most of our oceans, so the Atlantic and the Pacific, those are about 3.5% salt. The rest of it is just water. So there's about 3.5% salt in our oceans. But do you know how salty the Great Salt Lake is? Wow, some people love the Great Salt Lake just as much as I do. Our friends in Zoom told us 27%, and you hit the nail right on the head there. It is exactly, it's about 27% salt. So much, much, much more salty than the ocean. It's only because of that very specific amount of salt, or because of that extremely high concentration of salt to water, that we're able to form crystals. Because in order for crystals to form, you basically need a super saturated solution of whatever is making up that crystalline structure, which is going to tie together when we take a look at our crystal growing experiment over here. Now, last set of crystals I want to show you, or last set of minerals I want to show you, is right inside this case. Now, I said that I've been collecting rocks for a really long time. So I've been collecting rocks since I was a little kid, and I've got all sorts of carrying cases for my crystals. This is just one of them. I made the mistake of, when I was very young, not classifying a whole lot of my crystals and just keeping them. But as I've gotten older, I've realized the importance of labeling and categorizing and sorting my crystals. And so this is just one of my sorting cases that I have for our crystals here. So you can see that I've got some Canadian amethyst. So I like to note the type of rock and where it comes from if I do know that. Of course, I haven't been to all the places where these rocks are from, and so some of them I've purchased other places, but we also have ones that are native to Michigan. I'll show you my very first rock collection that I ever actually got, which is this one right here. Now, when I was on a field trip to Greenfield Village when I was in 2nd grade, I bought this set of Rocks and Minerals of Michigan, and I've actually never taken it out of the plastic. But this is, I think, what started my love for rocks, just because I thought they were very beautiful. And it was cool to know that all of these different types of rocks written right here on this sheet, these can be found right here in Michigan. My favorite one, of course, down here is not a crystal, but this is a Petoskey stone, which were deposited in here in Michigan by the glaciers, which formed our Great Lakes and formed the landscape here in Michigan. So these are very, very unique to us, but you can find all of these types of gems right here in Michigan. So if you live here in Michigan like I do, there is hope you can find all sorts of cool rocks, crystals, and minerals right here where we live. So I want to show you another resource. If you're curious about where you can find certain types of gems, there are tons of resources for this online. A very helpful one that I've found is this website, which is gemdat.org. And this shows you a map of the world and how it relates to how we find different gemstones. So this categorizes all the different mines and quarries and places where we found specific types of gems all around the world. So you can sort by type. So if you're curious about a specific type, so let's see, we talked about emeralds, those really, really beautiful hexagonal green gems. And you'll see that emeralds grow kind of in various places around the world, which tells us, you know, based on this map where we might be able to find them. That means that those environmental conditions must be just right in order for that type of gem to grow there. Of course, one of the most famous gems is a diamond. And you can see that diamonds have a little bit less of a broad range of places where we might find them. Most of the diamonds in the world are found in southern Africa. So this is actually part of the reason why we've developed ways to grow diamonds in a lab. It's because we call those ethical diamonds, so we don't want to get diamonds from places where we might have to destroy habitats or environments of either animals or people in order to get these gems, even though we find them very beautiful and they do have all sorts of uses for science and for other things. It's important that we don't destroy nature in order to get them. And so we've actually started coming up with ways to grow crystals in laboratories. So we call those ethical diamonds or ethical gemstones, which I think are just as beautiful. Even though they weren't grown in the earth, they were grown in a lab. So that's something to consider as you purchase gemstones. Is you should be aware of where they come from. And that map, that gemdat.org, is a great way to figure out where different types of gems might have been found around the world naturally. But let's talk a little bit about the uses of gemstones, because gemstones do have their uses in science and for all sorts of other purposes. Now, people, number one, think they're beautiful. So we're pretty familiar with people using gemstones for jewelry, but they can have scientific uses as well. We use them silicone crystals. You might have heard of Silicon Valley even. So silicon crystals are used in computer chips because of their structure, because they're semiconductors. They have really good properties of those crystals to be used as computer chips, whereas other crystals have different chemical properties, and so we don't use them for that. But one of the most important scientific uses of crystals is something you may have heard of before, and it has to do with something that we call X-ray crystallography. So that is a big set of hefty words, but basically in science, we can use crystals in order to take images of things that are very, very small, too small for us to see with our eyes or even with a very powerful microscope. So what we do is we actually take a crystal, a very, very small piece of a crystal, and then we send an X-ray, which is a type of light on our electromagnetic spectrum, through the crystal. Then that actually scatters the light in different directions based on that crystal's very specific structure, which we've talked about already. And then over here on the back, we have what we call a photographic plate. So based on the structure of the crystal, it will diffract the light differently onto the plate, and we can actually take an image of where the electrons orbiting those atoms are most dense. So these dark spots would be where those electrons are most dense. And you might say, well, who cares, right? But there is a very famous scientist and a very famous innovation that's important to all life on Earth, not just human life, but all life on Earth, which is because X-ray crystallography is what gave us the, or what helped us to discover the actual helical or double helical structure of DNA. So we might be familiar with two scientists called Watson and Crick, and Watson and Crick are largely credited for discovering the double helical structure of DNA. They basically looked at it as a puzzle and tried to figure it out based on logic, but they based all their studies on this scientist's work. So this is Rosalind Franklin. And without Rosalind Franklin, Watson and Crick would have had no idea how to justify their science and how they discovered the double helical structure of DNA. So this is one of those X-ray crystallography images that Rosalind Franklin took. So she crystallized DNA, a very, very small crystal of DNA, and used that process of X-ray crystallization or X-ray crystallography to take this image. Now, this image doesn't tell us a whole lot. There was a lot of math that had to go into this. So just to get this photo, it took over 100 hours of X-ray crystallography or X-ray diffraction. 100 hours to take one photo. But this doesn't exactly tell us the structure of DNA. Watson and Crick looked at this photo and, like we said, tried to figure it out like a puzzle. But Rosalind Franklin took the mathematical data from this image, from the darkest spots, which tell us are the most electron dense, and she took that information, and it took her over a year of doing math and calculations for her to prove that DNA forms this double helical structure. This was an amazing innovation, and unfortunately, Rosalind Franklin, she submitted her report. Since it took so long to prove this theory with math, she submitted her studies after Watson and Crick, which is why Watson and Crick are largely credited with discovering the structure, even though they could not have done it without this photo that Rosalind Franklin took. And so unfortunately, since Rosalind Franklin died before Watson and Crick were given the Nobel Prize, she did not receive a Nobel Prize because Nobel Prizes cannot be given out after your death. But her innovations have not been forgotten. We should always talk about the contributions that women have made in STEM because they are so important. There would be no proof for that double helical structure of DNA without Rosalind Franklin's photo, which we call photo 51. All right, so with that, let's see, what else do I have here? Oh, one of my favorite topics about crystals. So there is a great question that comes up, especially if you do any sort of research on crystals. If you were to Google the phrase crystal science or science of crystals, just as I know I did when I was looking for some research and some background information before this episode of Echo Live, the first thing that almost always comes up is the healing properties of crystals, is how people can use crystals in order to heal their ailments or to improve their medical conditions. And I think that's a very important thing that we should address here on Echo Live, because a lot of people love crystals and think they're beautiful. I know that I do. I even have this keychain that a friend made me, so I can carry some crystals around with me all the time. But it's important to talk about the science. Is there science that says crystals have healing properties? And the answer to that question is no. there is no scholarly science that backs up crystals having any sort of healing properties. But that's not to say that there are no benefits to crystals being used by people to improve conditions or to improve their mental health. Because there was a study done by that scientist who I put up here on the screen. So Dr. Chris French in 2001 decided to think about this question scientifically, to actually put it to the test in a controlled study. And so they got a large group of people, some of whom believed in the healing properties of crystals, and some people who did not. And so they had an even spread of people who felt both ways and some people who had no opinion of the crystals whatsoever. They gave half of their participants a real gemstone, a real crystal, and they gave half of the participants a fake crystal, one that was so good, like a good enough fake that you really couldn't tell the difference by looking at it. And they told everyone that they were receiving a crystal and they wanted them to record how those crystals made them feel, if they felt any vibrations, if they felt positively affected by these crystals. And at the end of the study, they found that across the board, everyone started to, not everyone, but many people, whether you had a real crystal or a fake replicated crystal, people felt those positive qualities of crystals. So that makes us think that, right, that the crystal themselves is not actually what's having the positive effect. It's that effect on your mental well-being. There's studies that show that the act of just taking a pill, whether it's medicine or sugar, can have positive impacts on people's health. That's because when you do that, when you have a physical sensation of helping yourself, of trying to improve your health or your quality of life, that your brain will actually release chemicals to help with that process. So there is no science that says crystals have healing properties, but that's not to say that people can't believe in them and their effects. So if you like having a tactile representation of something, if you like to hold on to something because it makes you feel good, there is science behind that as well. So it's okay for people to love crystals and appreciate crystals and believe in their effects, but crystals should not be trusted over modern medicine or medical advice from doctors. Just our PSA, the Michigan Science Center, of course, we love crystals, we love rocks and minerals. They have all sorts of uses in science, but healing is not one of them. All right, so the moment we've all been waiting for, I know we're over our time here, is we are going to grow some borax crystals over here. So what we are going to do, let me see if I can zoom my camera in. Perfect. What I have in this glass of water is, or this glass is some warm water. And what we need to do is create a super saturated solution of borax, which means there's more borax than could be dissolved into the water. So we'll start by adding, it's really just an arbitrary amount of borax, which is that powdered soap that hopefully if you watched our slime episode, maybe you already purchased some of this borax. And we're just gonna start mixing it into our warm water. Now we said we want to create a super saturated solution, and the easiest way to know that our solution has been super saturated is just once we start to see it accumulating at the bottom of the glass. So once we've added enough that it actually can't be dissolved into the beaker or into the water anymore, that's when we'll know it is super saturated and that we've added enough borax. It is a pretty large amount. It's about, let's see, I've reduced my quantity a little bit more than in my practice, but for about 400 milliliters of water that I started with, we'll want to add about 200 milliliters of borax. So about half the amount of borax as the water. But again, you'll know that your solution is super saturated once you can't dissolve any more of that borax into the water. So really start here. I can actually see that we are not having it really dissolve into the water any longer. Having warm water is the key to this, because having warm water, of course, we've talked about before, allows for more diffusion of the substances that we're dissolving in the water. Think back to our Kool-Aid or powdered lemonade experiment that we did last Friday. Having warm water allows the borax to easily dissolve into the substance. It requires less stirring. And then once it cools, all that excess borax will settle to the bottom. All right, so now that we've gotten it really, really dissolved in there, I'm actually going to pour it into a different container to allow our crystal to grow. So if we take a look down here on the table, I have just a glass mason jar that I'm actually going to grow my borax crystals inside. The beaker of water is really, really warm. So safety first always here on Echo Live. I'm putting on my gloves so that I can just pour our borax solution down into our mason jar. So we are ready to grow our crystals. Now, crystallization of borax works a lot like our Mentos and Coke reaction that we've done here on Echo Live in the past. We've talked about nucleation, which is the property of something to stick to these different pores. And so what we're going to use as our nucleation site where those borax crystals are going to start to form is actually a pipe cleaner. Now, if we want them to form into any specific shape, all we need to do is form our pipe cleaners into that shape we want it to grow into. So you could make your crystals or grow your crystals in the shape of your initials if you were to form your crystals that way or your pipe cleaner that way. But I'm just going to form kind of a nest type shape here, just kind of wrapping it around itself, forming it into like a little bird's nest made out of pipe cleaners. Now, you could use colorful pipe cleaners like I'm doing if you want your crystal to be multicolored from the borax, or you could use food coloring inside your borax solution. So I chose to do the colored pipe cleaners as opposed to the food coloring, but you can use either option. All right, so now that we've got a pretty large nest of pipe cleaners, you can see my little shape that I've created here, just really, really crisscrossing them back and forth. And that's going to allow the crystals a place to grow on. We're then just going to attach this to a popsicle stick or a coffee stirrer that I can place across the top of the glass. So the last thing I'm going to do is just add one of these pipe cleaners to the very top, kind of measure how far into the glass my nest will need to go in order to be submerged into our super saturated borax solution. All right, there we go. So it needs to be about that low. And then I'm just going to wrap my pipe cleaner around the coffee stirrer and submerge my pipe cleaners down inside. Now, normally, real crystals, like the ones we've talked about here on my table, take millions of years to form. What's amazing about our borax crystals is that this solution is so super saturated that this is actually going to form crystals overnight. And so we will get to show you these crystals tomorrow here on Echo Live. And I hope that you get to try your own. If you do have some borax at home, if you don't have borax at home, you can purchase this at any grocery store or big box store. So on your next essential trip to the store, buy yourself some borax, boil yourself some water, and try to grow your own crystals. If you don't have pipe cleaners, you could experiment by putting different types of nucleation sites inside your solution as well. You could use coffee stirrers like I have, or popsicle sticks, or string, or yarn. You can try all sorts of different configurations for your nucleation site and see what kind of crystals you can grow. So if you have any questions about what we've talked about today on our crystallography episode of Echo Live, let me know in the chat. I'm going to, of course, at this time, take a moment to thank the sponsors of the Michigan Science Center. We are very thankful for our sponsors like Ford Motor Company Fund and Denso, who allow us to bring these programs to you at home for free every single weekday. Of course, if you are enjoying these videos, please like, subscribe, and share these videos with your friends on Facebook. Share our YouTube videos. Keep tuning back in on Zoom. And of course, we'll be back tomorrow with even more Echo Live. So let's see if we got any questions. I saw a couple starting to come in. Will it work the same with salt? The answer is yes. But I showed you my salt crystals that I had from the Great Salt Lake, and they're just very brittle. So you can do this with salt. You can create a super saturated salt solution and grow your own salt crystals, but it's a little bit more brittle. Just the structure that those salt crystals form is not quite as strong or structurally sound as our borax crystals. But since it can form crystals, you can try that at home, certainly. So if you have salt and not borax, give it a try. You might need to add more salt to the solution than the borax in order to create a super saturated solution, because that is the most important part, that you have an amount of that substrate or that solid that you're pouring in settling on the bottom. Vanita has crystals at home. If you want to take a picture of them and share it with us, I would love to see your crystals, Vanita. That is super cool. I also have a lot of crystals. Maybe I'll line mine all up and take a picture of them for you all. How are crystals different than minerals? The answer is they're not. So crystals are minerals, just like anything is really a mineral. So all of my rocks in my rock collection, coral is a mineral, but all of the crystals are minerals. What makes crystals specific is that crystalline structure. So crystals are minerals, but they are crystalline. And so that is what makes them specifically crystals and not just minerals. Owen has made crystals at home. Again, if you guys have done these at home, please take a picture. Always, of course, tag the Michigan Science Center. We'd love to share your experiments. I'd love to see them. I love hearing that you guys are trying science at home. It is so important to do this and to stay engaged in science at home. Even though none of us are in school right now, it is super important. Stephanie asked, how do the crystals become colorful? I'm unsure if you mean in my growing crystals or in my real crystals here, but I'll answer both. In our growing crystals experiment, like I said, you can either use a colored nucleation site, like our colored pipe cleaners, or you can dye your supersaturated solution with a good amount of food coloring. But in real crystals, in the ones that form naturally in the earth, it's because of those different substances, those different configurations of atoms, or in the case of our amethyst, it's because of the imperfections in the crystal itself. So there are imperfections or molecules or atoms inside the crystal that are not part of the crystal itself. And when light hits them, it bends the light and it changes its wavelength and it turns it into visible light, which we can see. So it's very, very unique. Depending on what we're talking about, we get different colors. So we can get purple, green, pink, blue, any color you can think of. There is a gemstone out there that naturally occurs in that color or can be colored that way based on its impurities. All right. If you have more questions, feel free to keep sending them in the chat. I love hearing this. If you have suggestions for more episodes, definitely send those to us as well. We did this crystal episode because this is something you wanted to learn about, and I love that. I learned a lot, and I hope you learned a lot as well. We will be back here tomorrow at 2:30 for more Echo Live, and so I hope I'll see you all then.